Extrapolated interval.
Extrapolating.
Extrema.
The name of the game is follow the directions. Memorize your forever cards and follow the directions. Meaning, there are going to be days where homework is not due the next day, but I strongly advise you to do a very strategic part of it. And if you don't do a very strategic part of it, your life will be much more difficult when you go to finish the entire thing. These homework assignments, wait, are the beginning of applying derivatives. Now, okay, we did apply derivatives in related rates and tangent lines. Those are the two places that we've applied derivatives. How do you use a derivative to help you find a tangent line? Yes, so is the derivative the tangent line? No, it is one piece of the tangent line, right? It's the m in the tangent line equation. Okay, related rates. Related rates. How do you use derivatives to solve related rates?
Find things you don't know.
Kind of. You can't even deal with rates unless you have an equation involving rates. You can't get the equation involving rates until you derive, right? So a derivative is a key step to the process, but is the derivative the answer? No. But we use the derivative to arrive at the answer, right? A lot of breaking down, a lot of analysis, a lot of considering the situation, the givens, what you're supposed to find. But you use the derivative. Okay, chapter 3. What did I say that the title was, basically?
Function analysis.
Good, function analysis. Another way of saying it, if I was to actually minimize the notes and let you guys read the title of this notebook file, it's analysis of function behavior. Function analysis, analysis of function behavior. We're going to use derivatives to understand how a function moves, changes, behaves, etc.
Wow.
Now, in pre-cal, we did this without calculus, and we could only do so much. In pre-cal, we would talk about the end behavior of functions. What kind of polynomial am I right now?
Cube.
Maybe.
Odd.
Odd-powered, odd degree. With what kind of leading coefficient?
Positive.
How do you know that? Because we memorized it,
Yeah,
basically.
positive.
And we kind of use what we knew about an x cubed to generalize it for an x to the fifth, which could be out here with lots of hoops in between, right? If I was doing this, what kind of polynomial am I?
Any negative, even.
A negative leading coefficient, even degree. Could be lots of blah, 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 we don't even know, right? But what kind of polynomial could we, it's the only one we could have, could we have found the max or minimum? It's the only polynomial last year. Without a calculator, we could have found the max and minimum. A quadratic, because a quadratic has a vertex, and a vertex is either the
Max.
min, in this case, if the parabola is up, leading coefficient positive, or a max if the leading coefficient is negative. Do you remember how you had to try to graph like cubics and quartics and quintics using things like intercepts and sign charts and behaviors and maybe like vertical asymptotes and holes? You had to try to graph it, and I said, if you knew calculus, it would be so much easier, but you don't. So you can't. Were you able to perfectly find the maximums or minimums of anything beyond a quadratic without a calculator? No. Now, could you kind of get a few intercepts and be like, I think it changes around here and around here? Yeah, and know exactly, well, eventually what it's going to do as far as the end behavior? Yes. But in calculus, well, leading up just really quickly, can I just give you one of those really nasty cubic polynomials? I'm just going to give you the graph, not even like a function. I'm not even going to name it necessarily. But let's just take a graph real fast, just to give you a peek at what this whole chapter 3 thing is. And then we'll be going on extrema. So, what if I was to give you some sort of nasty cubic? Haha. Last year, in pre-calculus, if you were to find intercepts, pre-calculus, let's do green because it's review, right? If you were doing intercepts, how much of this graph would you have found? 1 point. Which wouldn't have been that hard because x is equal to 0, y is equal to, you could have solved for that. It's really easy to plug in x is 0, right? Because then you just solve and you say, hey, sweet, y is whatever's left. But if you tried to plug in y is 0, number one, you would have had to try to factor the cubic polynomial. You would have figured out, or maybe just gotten really confused, that this guy only has one real 0. Oh, could you have maybe found the guy over here somewhere? Okay, so if you've been able to factor that cubic polynomial, 2 of these zeros are complex zeros, so yeah, they would have been out there somewhere. This guy might be a nice 0. It might have shown up in our really cool possible zeros chart that we would have done with, remember, plus or minus factors of the last term over the leading term. Maybe this one would have shown up there. Or maybe it would have been like a nasty decimal one that wouldn't have shown up there. But, okay, in pre-cal, we could have found this and we could have found that. Would that have been enough to help us?
Yep.
Yeah, it could have been, right? You would have been like, okay. So you would have looked at the polynomial, and you would have seen that the polynomial was a third degree, right? If you had been given the polynomial, whoever he was, he's an x cubed. So then last year, what would we have done? Made a table and done sufficiently many solution points. We would have been like, what's going on there? And what's going on there? And what's going on there? We would have, okay, maybe found a point and then maybe found a point. So we could have plugged and chugged, right? And would we have known that this, because it would have had a positive leading coefficient, would we have known that it needs to go down forever? Yes. So maybe we would have guessed, and then maybe we would have guessed, and then maybe we would have guessed, but would we have gotten it perfectly? No. Not without a calculator. But in calculus, what can we do? Do you notice anything special as far as a derivative and tangent lines that's occurring at the high and lows? The slope is 0. Oh. So if I just take my derivative and set it equal to 0, and if I take my derivative and set it equal to 0, could I find my maxes and mins now that we know calculus? Now, how are we going to know who's who? Well, if we were to start graphing points, and if we were to look at our cubic polynomial, okay, then maybe we could have figured out that that needed to be the max, this needed to be the min. Maybe we still would have graphed 1 or 2 points just to have a point of reference, but we would have known, hey, got him. There's my third degree polynomial. But guys, have we only been seeing polynomials in calculus? Aren't those like the easiest derivatives ever? How hard have derivatives gotten?
So hard.
Why? What else are you seeing besides polynomials? Okay, you're seeing inverse trig. You're seeing trig in general. You're seeing square roots of radical functions. You're seeing rational functions, quotient rules, right? You're seeing logs and e to the. Is everything as easy as a polynomial? No. Now, do we have some basic ideas about some of these guys?
Yes.
Yes. But have they gotten way harder than, or putting multiple ones of these together with powers and fractions and roots? So we have an idea of some of the pieces, but put them together, and how does that work? Polynomials are going to be one of the easiest types of functions to graph, and calculus makes it all the easier, because if we can just set the derivative, wait, why does that make everything better? The cubic polynomial, we might not know, but if you took a derivative, what kind of polynomial would it be? A quadratic. Am I supposed to be able to find the zeros of a quadratic no matter what? Yes. Now, if this is a 4th degree and this is a 3rd degree, maybe that wouldn't be so fun. We might have to use some of these factoring tricks after all. Or if it was a 5th degree and we were trying to set the 4th degree equal to 0, once again, it might be nasty. But long story short, last year, polynomials, super hard to graph. Why? Because we had no non-calculator way of finding the max and mins. But then this year, it's like, oh, by the way, the derivative is 0 there. So just take the derivative and set it equal to 0, and you can find any maxes and mins. We'll talk about that. So, maxes and mins. Extrema. Oh, extrema. What word do you guys see in extrema? Extreme. And what does extreme mean?
Wacky.
Highest and lowest, maybe?
Perhaps.
Wait, highest and lowest, maximums and minimums. I was introducing extrema by talking about what you remembered from last year. My honors pre-cal kids, you did an actual worksheet where you said something like, for all these different quadratics, this one has a maximum value of at, or this one has a minimum value of and at. It's going to be helpful this year. Right now, there are different types of extrema. Some of them are absolute and some of them are relative. Absolute versus relative. Where have you guys heard those words used? Life. What part of life? You should have heard it by now.
Everything's relative.
Absolute and relative.
Absolute truth and relative truth.
Yeah, that's the most common example. Like in philosophy classes or ethics classes. Relative truth versus absolute truth. Well, I'm not sure it's entirely a thing, but it's definitely not as much of a thing as our rules. Anyway, coming back. Logically, rationally, it doesn't make sense for it to be. But, those happen to be. Or Mr. Carmichael. Also,
PC.
Did he used to teach seniors?
Yep.
he did for 1 year. They needed him to like fill in one class. I think he's gonna teach me. He's so cool if he can do it all. Coming back. Absolute versus relative. Thinking about truth. Absolute truth versus relative truth. Absolute truth is talking about something that is always true no matter what. Right? Absolute, absolutely. Absolute, absolutely true. Okay? Relative. Depending on the context, depending on where you are, depending on who you are, depending on how you're feeling, depending on how the people around you are feeling, depending on circumstances and culture and identity and whatever else you want to put into that category. Political party? Sure, why not? Anyway, relative, it depends, right?
Yeah.
Okay. So, starting off with absolute extreme values. This is what you guys are taking notes on. Abby, why don't you start with this? Or you can look at it. Absolute extreme values. Extreme, check it. Isn't this an adjective?
Yes.
What kind of values? Extreme values. But what's this?
A verb. Noun.
A noun. So, extreme values, values that are extreme, values at the extreme. We use extrema to be the noun. Okay? So, extreme values just kind of describe what extrema are. The absolute highest or the absolute lowest on a curve or a given interval, also called global extremes or the extremes. And then the whole little like continuity affects existence. Let's look at the examples. Why am I putting this whole little continuity affects existence? Basically, these examples are showing how this is true. Do you guys see how these ones are including the endpoints, right? Including the endpoints and the endpoints exist. This one is excluding the endpoints, and maybe they don't exist, maybe they are truly holes, or maybe they normally are there and we're just not allowed to look at them because it's an open interval. And then this one is including the endpoints, but excluding the, oh, they've put a hole in the middle. There's a hole in this cake. Anyway, how do those discontinuities, whether they're actual discontinuities or whether they're just being ignored because of the intervals, how do they affect the existence of maximums and minimums? This one on the far left, continuous. Continuous and including everything in between and the endpoints. So it's continuous at the endpoints and everything in between. Is there an absolute min?
Yes.
Yes. You're looking at the y values and saying, is there a lowest point on this curve? Most definitely, and it's right there, right? So is this a min? Yes, but it's not just a min, it's also the min.
Amen.
It's a min, not a min. It's a min of the area surrounding it, therefore it's called local or relative, but it also is the absolute min or the very lowest point for the entire curve. Now, really quickly, what kind of min is it? It's a min of, well, how low does it go?
1.
To 1. That's the value of this function at 0. How low does it go? The minimum value of 1 at or when x equals 0. Does that make sense, the difference? X equals 0 is where this happens, and the actual lowest it goes is 1. When I'm talking about min or max values, I'm talking about those y values. How high, how low does my function go? So do I have an absolute? Yes. Do I have a relative? Yes. Okay. How about this guy? He's an absolute. The BC book this year would actually also say that he's relative, because kind of like the definition of continuous, if it's a closed interval, we ignore that side. So it would say, well, it's the highest of this little baby region, it's kind of a relative, but no. We're just going to call it an absolute, because if the function were to keep going, he would not be the lowest, or I should say the highest, of the region around it. So we're only going to call him an absolute. We're going to call him the max. So yeah, there's a max, and it's right there. And once again, we could go ahead and fill in and say the max of, how high does it go? 5. And what's the at going to be? 2. Does that make sense, the difference? The value is 5. How high it goes is 5. And that occurs when x is 2. Now, question. Why does this one say no longer a max?
Because it's open.
But I still see it. So why don't we just go one step below? What's one step below 5?
4.999.
See the problem? You say 4.9, I say, what about 4.99? You say, well, what about 4.99? I'm like, exactly, 4.99. There is no highest. Because this is going to be forever approaching the max cap of 5 that cannot be included. Why? Maybe there's a hole. Maybe there's a vertical asymptote. I mean, there's not. It's a parabola. But in this case, it's open, so we're not allowed to actually use it anyway. So, is there a max? No. But is there a min?
Yeah.
Yes, because the endpoints, only one of the endpoint was an extrema. The other, minimum, the possible maximum was at an endpoint, and then the minimum was in the middle, and there's nothing wrong in the middle. So therefore, yeah, there still is a min there, and also the min there. Okay, how about over here? What made the min not exist? It's a hole. If you were to actually come up into the function, and if I was to plug in 0 where the min should be for this parabola, is it actually at that low point? No, it's somewhere else entirely. So is that the lowest? No, that's where the lowest should have been, but when they made it a hole and filled in the point, well, no. No min. Why don't we just pick something right above 1? Exactly, the same problem. Point, no. Oh, no, 1.01. We would never be able to actually be just 1 anything right above. We can't just get the one closest value. There is no closest value to 1 that we could choose. So, what's going on? F was continuous on a closed interval. There was a max, the max, and there was an absolute min. This one, F was continuous on an open interval, but we lost one of our extrema because it was at an endpoint. This one, it was a closed interval, but this function was not continuous. We lost one of them. This kind of poses a problem because AP questions love to ask at least once or twice a long answer or multiple choice, maybe both, for absolute extrema. So how do we find them if it's a much more complicated function than a polynomial? Well, before we talk about how to find them, let's talk about the other guy. So absolute highest can happen at endpoints where you cut a graph, or it can happen at natural curvatures. But then the other guy is the that I put on the page before, max, min. It's the local or relative extrema. They occur at the highest or lowest values contained within an open interval. It doesn't need to be the highest or the lowest of the entire function. It just needs to be a highest or a lowest of a little region around it. Now the around it is important. In VC it would say, well, kind of around, but we kind of redefine. But in AB, we're saying, no. It needs to be for a region around it. So a little bit to the left, a little bit to the right. Is it the highest? Is it the lowest for that little baby region? Whether or not it is absolutely for the entire function. Have you guys get the words? I'm going to zoom in on the examples. The main point of the examples, to be totally honest, is just sort of the sketches. So don't stress too much about getting all the information. TBH, it doesn't really matter.
Before on the first one, didn't we put that for the max? Like, why wouldn't we,
not a max, it's not a relative or local max, because if I was to take a region around it, I don't have the other side to consider. And if I did, it would not be a high or a low. Does that make sense?
So only if you know what's around it.
Right. For this year. For next year, Adam, we would say, since we don't know everything around it, we can still call it a relative. But it kind of distorts the meaning of a relative extrema. If we do it that way. Because yesterday was the first time. Yesterday was the first time.
Wednesday, my dude? What is this going to bring? The last
2 weeks. We have 2 full weeks after this week.
Yeah, we have 2. This week, we have 4 days and then 5 days?
Oh, I mean, just 2 full time-wise, not so much school. You guys have the whole local relative. Can I zoom in on the graphs?
Is spring break early March or late April?
A week after. No, before Easter.
Yeah.
But that means football. That means football.
Well, Kyle.
What?
That's really.
Is next year a leap year, Misty?
As long as me and my dad on the same spring break, I'm fine. Because we might have the same spring break.
Is it multiples of 6?
4.
Oh, yeah. Leap years.
Yeah.
There's a college fair on leap year day.
That's fun. That's random.
Sorry.
Where is Rachel?
College fair. Yeah, I think I went to a college fair. Sophomore.
It's been a great year.
Hey guys, do you remember how just a second ago we had some polynomials? And those polynomials, I was like, you know what? We can find any of their maximums or their minimums by finding the zeros of the derivative, right?
Yeah.
This relative max of a, not quite a polynomial, it's a little bit more complex, but doesn't that max still occur at one of those zeros? Right? So that'd be an HTL, that would be, check it, the derivative of 3 is 0. Good. And this guy, I mean, he's trig, he's sine, but aren't all of his peaks and valleys? Oh, too bad we didn't learn calculus before we learned sinusoidal waves. We could have just found derivatives and then set them equal to 0 to know all of the peaks and valleys.
Cosine.
Instead of our like sinusoidal axis and our amplitudes and our periods and our, anyway. But sine and cosine, aren't those also going to be those nice horizontal tangent lines where the derivative is equal to 0, right? If you only saw nice little curves like this, okay, the functions are getting nastier, but still nice little curves. You're like, hey, all relative maxes and mins, which are sometimes maybe absolute also, are going to only occur at the zeros of derivatives until you get to this function. That's not a smooth turn, is it?
No.
If that's not a smooth turn, does that have a derivative of 0?
No.
Nope, there is no curvature. I don't have a horizontal tangent. I have a slope is -1, slope is -1, slope is -1. Ah! Slope is +1. What happens in between? Ah!
Where was?
Sharp point mean?
Who?
The derivative of the piecewise goes blue because derivatives have to agree from both sides because derivatives are ultimately limits, remember? And limits have to agree from either side. Do these slopes agree from either side? No! Therefore, the derivative does not exist. Oh, no! So when can relative extrema occur? At zeros? Yes. At sharp points? Yes. Uh-oh. So at zeros and DNEs. I wonder if they always happen at zeros or DNEs, or they just could happen at zeros and DNEs. Don't worry, we will answer it soon. But so far, what have we seen? Is this guy relative to a certain little region around it? Yes. A relative high? Yes, but he's also absolute. Why? Check out the function. It just keeps going and it just keeps going. Isn't this the highest? Question. If I'm looking at the entire domain, so negative infinity to infinity, is there going to be a lowest?
For what?
An absolute min. Why not? What's he doing? He's going down forever. So he has an absolute max. It's right there as a relative, but he does not have an absolute min. How about this guy? If we were going on his entire domain, is this an absolute min as well?
No.
An absolute min as well?
Yes.
Because
It ain't going any lower.
it's not going any lower than that. Yeah, so we can say absolute, but what does it not have?
Absolute max.
Yeah, it's not going to have an absolute max. How about this guy? If he was to keep on going and going and going and going, wait, what does sine do?
Bounces off the 1 to 1.
These are relative because it's the highest of the little baby region around it, lowest of the little baby region around it. But then look about or think about the entire curve. Is this an absolute?
Yeah. If 2 plus 2 is 5.
Is there a highest that sine goes?
Yeah.
Yes, and what is it?
1.
Is there a lowest that sine goes?
Yeah. Maybe 1.
Where did you guys get confused? How many times does it happen? A lot, infinitely many. Technically, it's going to hit 1 at every pi over 2 plus 2 pi n, right?
Yes.
Because you have to get like a full cycle to get back to that highest. And then there's going to be an absolute min infinitely many times, but I still have absolute min values. It has a highest and it has a lowest. Just is going to happen in lots of different places. Anyways, yep, absolute and relative.
Nice.
What made these guys not have a max and not have a min? What interval were we looking at? Open or closed?
Open.
Because I said think about his entire domain, right? And I said think about his entire domain. So how long was he allowed to keep going? Forever. And so what was he doing forever? Increasing. How long was he allowed to keep going? Forever. And so how long was he going to keep decreasing? Forever. But if I was to cut it, would there have been a highest?
No.
If I was to cut it,
Yes.
yeah, right? Because if I was to cut it and these arrows weren't allowed to go on forever, if I was to make some sort of closed interval, I would cut it, and wherever I cut it would be the highest of this guy. Or wherever I cut this one would be the lowest of that guy. Wherever I cut that wouldn't make a difference because he's not the highest or the lowest. But that guy, his left endpoint would matter. And this guy, as long as I did it symmetrically, as far as like a negative A to a positive A, they would be the exact same. But if I was to cut one guy here and one guy there, well, ooh, we're realizing maybe it's a little bit trickier than we first thought. Okay. Yep. To talk about extrema, one of the most important words that we have to remember are critical numbers, or the BC kids might call them crits. Critical numbers, or crits. Do you guys see an application of derivative in this card?
Yes.
Let f be a function that exists. First of all, the function has to exist. If he has holes or vertical asymptotes, kind of like all bets are off. We have to be a bit more careful. But if a function exists, and even more specifically is continuous, if f prime of c equals 0, oh, the horizontal tangents. Yeah, we just saw lots of those at maxes and mins. Or DNE, oh, the sharp points. The sharp points, we gotta look out for those because absolute value has a sharp point min instead of a nice smooth curve min. Then C is a critical number of f. Now, am I saying C is a relative max? No, because that's only sometimes. Am I saying that C is a relative min? No, because that's only sometimes. Right now, I'm just getting vocab down and saying, hey, you know what? Those maxes and mins seemed to occur at the zeros and DNEs of the derivative. So I think we better come up with a name. Don't worry, someone else already did. To describe those guys who are going to be my candidates. Ooh, candidates. Come on, my AP Gov people, candidates. I guess you can just not be talking about government and still think about candidates.
Hopefully you're just an American citizen.
Nice, Kyle.
What are candidates?
People who are
Not necessarily put themselves. True candidates are only ones that are
chosen.
No.
The claw.
Like able to be chosen.
because you can always write into a ballot, right?
Willing.
Willing to be chosen.
Someone
I
can
guess
be
it's
willing
anyone.
and not.
Anyone can be
35 or
They meet
older
the
American
requirements.
citizens.
As long as they meet the requirements. There you go.
National Guard
But if it meets
citizens.
certain requirements, even if you're looking for a job someday, right? Job candidates or
Not
application
now.
candidates have to meet certain, we could say college admission candidates. Anyway, candidates, right? Okay, we'll stop. Candidates. They're the ones that meet the requirements and so are able to be legally considered. Now, are there every now and then outliers for like life? Yes. Math? No. Critical numbers. I want you guys to write yourself a little note underneath. They are the relative extrema candidates. And actually, you know what? That's so important. I'm going to come up and have my boxing golf it.
Nice.
It's going on the forever card.
I have a question. What are we doing in the homework? Because I haven't seen any, like,
Oh, yes, you have.
kind of, but like.
How can you find the candidates? How can you find the critical numbers if you don't find the derivative first and set it equal to 0 with DNE? Wait a minute, let me help you with zeros and DNEs. How do you set something equal to 0? Okay, we've done that before. It's called x-intercepts. But how do we set something equal to DNE? How do you set something equal to DNE? Because if candidates, these critical numbers are the candidates for relative extrema, and if that's super important for knowing function behavior, function analysis, how do I set something equal to D and E? Okay, it gets a little bit tricky. But let me give you one hint for one particular type of function. If you have a rational function, now I know that's not every single possible function out there, but if you have a rational function, where do DNEs show up? What could make a fraction not exist?
Over 0.
Good. So if we can set, if something has a denominator, I can set that bottom equal to 0. If you want to think about it, it's like we're taking that single fraction and we're splitting it up into two pieces and saying, hey, let's look at that h of x and say you can't equal 0. Those are going to be my DNEs. And then let's take g of x separately. Let's set him equal to 0, and he's going to be my zeros. This might kind of remind you of last year when we were graphing, solving nonlinear inequalities. We talked about things like key numbers. We had set this little like number line and test true or false for these different intervals. And we had rational functions. We had to find the zeros. And I think I just called them vertical asymptotes back then because we'd already gotten rid of the holes. But we had to go ahead and take the key numbers, the zeros and the undefined points. We did it last year for inequalities when we had like fractions less than or equal to like a number or a 0. This year, though, we're doing it with derivatives in critical numbers. That whole key number thing from last year was to prepare you for this. This is forever card number 20, yeah? Oh, dear. How did that happen?
You know,
It happens every year. Just no one usually thinks
but
about
you
it.
realize, see,
Of course
it's
it
going to be
happens. John's
on
calculator is
420, it's
Okay,
going to be 420s.
What? Oh.
No, you're
420,
Oh.
20.
Gail for president.
Gail.
What if it was Abby making
Making
out
all
of
the Hunger Games.
They can't be, because she'll be 35.
Gail was the guy, wasn't it?
It was the
What's the
guy.
one
The one who was like cuter and you kind of wanted him to win. But then...
Yeah. Liam Hemsworth. Addie's Gail. Liam Hemsworth.
Okay, shh.
Toby?
Here we go. If you guys ever see dotted lines, stop focus. If you ever see dotted lines, it's just trying to show you exactly where this x value hits. It's not an actual part of the graph. It's just saying, hey, A goes here, B goes here, C goes here, D goes there. It could be a real function. It has to be a piecewise, though, I think.
Yeah.
Or get that test.
Go.
Yeah. Okay, so, question.
I'll show
First
it.
of all-
I'll show it.
Shush. At A, just too busy. He's an endpoint. That's not calculus. That's just he's an endpoint. At E, he's another endpoint. This guy has been cut. And I am considering from closed interval A to B, and I know that because A is filled in, sorry, A to E. A is filled in and E is, oh no, I don't want to do that. I didn't like that. I hit it.
Yes, A, B, C, D, E. A to E.
So, it's a closed interval from A to E. You're including A and you're including E. Okay? A is an endpoint, E is an endpoint, and these guys, ooh, are any of the other guys critical numbers? Are any of them HTLs or sharp points? Or non-existent points?
I can't tell if D is a sharp point.
Is B
No.
It's B.
B is not a horizontal
Oh,
tangent.
yes, it is.
Oh, it is.
E or C
Yeah.
is another horizontal tangent.
Yeah.
Yeah.
That one.
D.
Okay.
Oh, 0.
So this one is F prime equals, what am I talking about? B. That's a 0. This one is F prime of C equals 0. This one is F prime of D does not exist. That's a sharp point. This one is an almost 0. I would almost call this guy a critical number, but he's not quite at the bottom. It has to be a lot more obvious for me to call him a critical number. That guy's definitely not a critical number because isn't his slope like some obvious positive value, right? That's sloped up, and if you guys look at him, he's sloped down. Not very sloped down, but he hasn't quite gotten all the way down. Okay, so these two are endpoints, and these guys are critical numbers or critical values. Different ways of saying it. Question. Which of these, A, B, C, D, E, maybe one, maybe more than one, is a relative max? Which of these is a relative max, just looking at the graph?
B.
Yeah.
Oh, yeah.
Anybody else?
This D is high.
D is the highest of his region around him, isn't he? But what else is he?
Absolute.
He's a relative
Oh,
who's
so
also
it's
an
kind of like
absolute.
that square rectangle.
Is he an absolute?
No.
No.
So it's D. It's D. It's kind of like that square rectangle, where square is a rectangle, but rectangle isn't a square.
Now, are there any relative mins?
E.
E and BC would call that a relative min because we can't include, but technically,
C, yeah.
Kyle, we don't know what's under this image.
C.
C is a relative min. Question, is there anybody who's neither?
A.
Ah, no, A is an absolute.
Oh.
But you're right, he's neither, like he's not a relative in any way, shape, or form, but he is an absolute. Is there anyone who's like none of the above?
E.
E is nothing for the little guy.
Wait, what was D?
A relative max. Okay, some of you are like, how do we do homework from this? Well, you have a lot of the vocab, you have a lot of the
Come to class.
ideas. My advice is catch up in other classes and be ready to do math tomorrow. Because we're going to see tomorrow how to actually do homework. Huh?
Is there any homework to do at all?
Possibly, I don't have it memorized. I'll peek at it and comment. Adam,
How far do you look around?